Hi everyone, this is a follow-up example on relative atomic masses. So we have the following learning targets, still the same: calculate the average atomic mass, or solve problems regarding average atomic masses. Okay, so we have this follow-up problem to the ones we had in silver. Alright, so now we will be dealing with boron. So boron has two naturally occurring isotopes, and we are asked to find the abundances, percent abundances of boron 10 and boron 11, given that the atomic masses of boron, or the atomic mass of boron, is 10.81 AMU. So the relative atomic mass is already given, okay, or the average atomic mass was already given, which is now 10.81 mu. All right. And then what we do have are the isotopic masses of boron 10 and boron 11. So if we try to arrange the information that we have, this is boron 10. Its atomic mass is 10.0129 mu. And then this is boron 11, which is 11.0093 mu. Okay, and then we are asked to find their relative abundances. So the percentages, each percentage. Okay, so that means we are going to find out how many percent is boron 10, how many percent is boron 11. So I think it would be safe if we, from the given atomic masses, then we have to calculate first the fractional abundance, and we can convert the fractional abundance later on into relative abundances. All right. So in here, we do not, let's say we do not know the fractional abundance of B, so we can assign it as our X. All right. Now, if we have our X here, what should be the designation for boron 11 or 11b? Okay, so take note that the sum, okay, the sum of the fractional abundances in here is actually 1, because we are dealing with percentages. Okay, so it's just like simplifying 100% into 1. Okay, therefore if you try to add, let's have this in our line of reasoning. So in order for us to get b, 'di ba, we take into account this is in terms of fractional abundance. uh, we take into account the contribution of 10b and 11b, right? So in terms of fractional abundances, this gives us 1 or 100%. And then let's say fractional abundance lang, this is, we assign 10b as our x, and therefore our b11 is our y. We do not know these values. Therefore, we can say that y is equal to 1 minus x. Okay, so therefore in the designation for fractional abundances, we can actually place 1 minus x in here. All right, 1 minus x. And we know that in getting the relative atomic masses, we have to get their portions or the contributions for each isotope. So since we already have the relative atomic mass, which was our answer in the previous example a while ago, so we can just write it directly. This is 10.81 mu, or atomic mass units, is equal to, so we include these terms, so 10. Okay, just like what we did in the previous example. This is for boron 11, or for boron 10. For boron 10, we have 10.0129 mu times its fractional abundance, which is x. All right, and then it, for boron 11, so we add, right, we add their contributions. So for boron 11, this is 11.0093 mu times 1 minus x. All right, so this is how it goes now. We are taking into account the contributions or the weights for each particular atomic, for each particular isotope. And so if we simplify this, this is still 10.0129 mu times x. Then we can distribute this term, okay, to 1 and to x. So that means we have 11.0093 mu minus 11.0093 mu x, right? And then we just have to simplify this equation. So we know that the final answer, or the one at the left side, is 10.81 mu. So if we solve for x, okay, we can actually have 11.0093 mu. Since we transpose it to the other side, this becomes negative. So we just have to subtract it from 10.81 mu. All right, 10.81 mu minus 11.0093. And then we have to simplify this one. 10.0129 mu times x. This is minus, okay, 11.0093 mu times x. All right. And so what do we have for x? 10.0129 minus 11.0093. So what we can get is 0.9 rather, 0.9964 x. And this was negative. This is still mu. Okay, so negative 0.9964 mu x. Okay, and on the other side, okay, 10 minus 11, so that is basically negative 0.1993, and then mu. All right, so negative 1993 mu. So if we divide both equations, so take note that we are looking for x, we divide both equations by this value. So negative 0.9964 mu. So that we can cancel. So this one also is divided by 0.9964 mu. All right, and so we end up with our value for x, which is 0.20 something, 220. All right, and then therefore our 1 minus x, the value for 1 minus x is 0.80. Okay, so that just means it's 1 minus 0.20. Okay, so our final answers will then be for the relative abundances. We just have to convert them into percentages. So times 100 times 100. Therefore, the relative abundance of 10 boron, since it was our x, is 20%. Okay, and the relative abundance of 11 boron is 80%. Okay, So out of the information given, we now have identified the relative abundances for each isotope. All right? So that ends our discussion for this example. Thank you very much for listening.